right, so today in class we're going to be talking about, or tomorrow rather, in class we're going to be talking about the history of the atom. And it's really important for you guys to watch this lecture because we're going to be doing a little bit of math with isotope calculations. So you guys remember that when we talked about the mass number from yesterday's lecture? Yes, yesterday's lecture that you were supposed to watch. We talked about like isotope abundance and how that's used to calculate the mass number, right? Or the atomic mass, and that's different from the mass number. So, as you're due now, we want you to answer the following Regents questions. Number one, in comparison to an atom of fluorine 19 in the ground state, an atom of carbon 12 in the ground state has 1, 2, 3, 4. Number two, state in terms of subatomic particles how an atom of carbon 13 is different from an atom of carbon 12. And number three, what are carbon 13 and carbon 12 called? So I hope, given the framing that I just gave you, all of these three questions have something to do with isotopes, hint, hint, and we'll be going over the answers in class tomorrow. So with isotope mass calculations, when we want to calculate atomic mass, and we get those weird little decimal points, right? Over here we have lithium isotopes. Okay, so there's lithium 6, where its atomic mass is 6.02 and its natural abundance is 7.5%. So it's less abundant than lithium 7, whose atomic mass is 7.02 and whose natural abundance is 92.5%. So hopefully we remember that the atomic mass of lithium, or sorry, the atomic number of lithium is 3, right? And so as a result, the isotope of lithium 6 would have 3 protons and 3 neutrons, whereas the isotope of lithium 7 would have 3 protons and 4 neutrons. All right, so in order to calculate this mass number, right, with isotope mass calculations, all we want to do is we want to multiply 6.02 times 7.5. Also, sorry guys, I'm writing using my trackpad, so this is going to be really messy. But 6.02 times 7.5%. Always remember this number is a percent, all right, aka a decimal. And so you always need to divide this number by 100. So 6.02, I'm going to enter this into my calculator, times 0.075 equals to 0.4515, all right? And we're going to ignore significant figures for the time being. And then 7.02, if I want to calculate the mass that this lithium ion contributes, or this lithium isotope contributes, my bad, I just multiply across the table. So 7.02 times 92.5%, just so I remember to convert to decimal, okay? And so if I enter into my calculator 7.02 times 0.925, I get 6, my bad, 0.4935, okay? So my last thing that I need to do in order to calculate this mass number is add these two numbers together to get the correct number, okay? Because 7.5% of my lithium sort of mass number that I see within the periodic table is coming from isotope lithium 6, whereas 92.5% of my mass number that I'm getting from my periodic table is coming from isotopes of lithium 7. So when I sort of quote unquote average it out, I get 0.4515 plus 4935, which is, hang on, let me enter this into my calculator, 6.945. So my average mass, depending on my lithium isotopes, of all my lithium isotopes that exist in this universe, is this number, 6.945. All right, so we'll walk you through one more example. Here is this element, Z, okay? So we see there's an isotope of Z4, whose mass is 4, okay? Z5, whose mass is 5, and Z6, whose mass is 6. So same type of deal. We multiply across and we add down, okay? So first, we want to multiply across. And I want you guys to treat this like we have another column over here. All right, so 4 times 90% is the same as 4 times 0.09, or not 0.09, my goodness, 0.90, okay? So this equals to 3.6, okay? And then next, multiplying across, we have the isotope Z5 has only 8% natural abundance. So 5 times 0.08 equals to 0.4, okay? And then lastly, we have isotope Z6, which has even less natural abundance. We have only 2% natural abundance. So over here, we take 6 times 0.02 equals to 0. Oops, whoa, that's a crazy 0.12. So total, if I add these together, I get 4.12 is my average isotopic mass for all of these isotopes of Z. All right, so last example, again, I'm just going to draw a column over here. I have two isotopes of element X, all right? I have isotope X50 and isotope X75. So once more, I remember to multiply across and add down, all right? So I'm just going to draw my equal signs and my plus sign just to remind myself, all right? So over here, this is my mass, 50, and I see it has 60% natural abundance, so 50 times 0.60 equals to 30, all right? And then isotope X75 has 40% natural abundance. So I multiply 75 by 0.40, and I also get 30, right? And so now my average isotopic mass for my average mass is 60 atomic mass units. Okay, don't forget your units. I haven't been writing it, so badness son. If you all were in here, I'd give you candy because it was my bad. Anyways, okay, so again, in class, you guys are going to learn about the history of the atom. Sorry to subject you guys to math in this way, but hopefully the multiplying across this table and adding down made sense for all of you. Oops, I forgot this little plus sign. So make sure you have this down in your notes just so you know how to do these calculations, and I will see you guys tomorrow.